In today's presentation, we're going to talk about the media itself, copper, fiber, as well as the wireless media. As a quick recap though, last presentation we discussed the different port types, whether copper or fiber, and when selecting hardware, this is going to be directly impacted by the media being used. So to have a better understanding of the media is why we're having this presentation today. And we discussed some of the nuances of both the solid conductor versus stranded, benefits of fiber, but in this presentation we're going to deep dive into this so that you can make the right choices and use some of the best practices in the industry. Again, as mentioned in the previous presentation, solid conductor, shielded twisted pair, as well as unshielded twisted pair has a maximum distance limitation of 100 meters per network segment. This is from switch to switch, switch to end device, or end device to end device. When using stranded category cable, do note that stranded category cable is derated down to 80 meters and should only be utilized for patch cables or shorter segments. For any long runs, use solid conductor and make sure to use shielded twisted pair for anything that's exposed. When running longer runs, unshielded twisted pair is acceptable if being utilized in its own metal conduit. And obviously, the cable quality and the category rating is critical for higher speeds. So while category 5 is good up to 100 megabits, you will need at least a category 5E cable for anything that is good up to 1 gig. For new installations, category 6 or better cable is recommended to ensure that your installations will meet tomorrow's needs. And while we're speaking of category cable, category 6 or better is recommended for PoE and PoE Plus applications due to the larger gauge conductors as opposed to category 5 or 5E. For applications with an MCC, look at 600 volt AWM rated cable. And for applications that are tray rated, look for a 600 volt tray rated cable if that Ethernet cable is going to be laying next to or close to a power cable. Also look at your environment and the necessary jacket material that you will need in order to withstand those environments. UV and oils are exceptionally hard on cable jackets. So as a result, look at PVC, PUR, TPE, low smoke zero halogen, or the necessary jacket material that is going to be tolerant of that environment. And because 35% of network failures are attributable to the physical media, make sure that you make the right investment and make the right choice. It's a whole lot cheaper to pull the media once as opposed to having to pull it out and pulling new media. And it also needs to be noted, not all cables are made the same. So one thing that Belden offers, as an example, is Belden offers bonded pair. Noise can invade non-bonded pair, as shown in the illustration on the left, wherever you have a gap. Because bonded pairs do not shift when being pulled or pulled around corners, and they don't create gaps, they have a greater immunity to noise while also having twice the pull tensile strength as compared to most other non-bonded pair cables. When making your cable, it's paramount that you ensure that the cable is terminated to the right standard. And when it comes to terminating the RJ45, it is the T568B wiring termination standard that is significantly more commonly adopted as opposed to the 568A standard. When making your own, make sure that the connections are tested and certified, making sure that all of the wiring is mapped correctly to the appropriate pins, and if at all possible, make sure that you use a proper cable tester that ensures that the cable is terminated correctly to support 100 megabit, gigabit, or even 10 gig speeds. A port link light or a pink test alone is just not enough. This here is a cable sample from a customer site. Their complaint was that their drives were periodically having communication issues. And when asked if the cable was tested, they touted, "Why? I got a link light and I was able to ping the drives from the PC. So it's got to be okay." So admittedly, while this is wired correctly and while this will give you a link light and it will support pings, this will not support sustained data speeds. The lesson of the story here is to use a level 3 or better tester. Spending $1,500 is not too much to spend on a quality tester, especially if you will be terminating a fair number of cables yourself. In a pinch, the RJ45 is an awesome solution in terms of providing a quick and easy fix. The downside is it's a single use. It does require the use of a crimp tool. If you don't have this crimp tool, unfortunately you're not going to be able to terminate this. But the benefits are that this is typically in stock at Lowe's, at Home Depot, and the majority of electrical distributors. Obviously, the note there is to test and or replace this in the morning, but it will get you out of a bind. Better yet, there are field installable, tool-free terminations that are very cost-effective for a quick fix. Obviously, the con for this is that it is not a cost-effective solution for bulk terminations, yet it does not require any tools, it is reusable, and it results in minimal cable loss when replacing an RJ45. Better yet, opt for pre-terminated verified patch cables, even if an overly long patch cable, and ensure that if you're going to terminate or re-terminate any ends, that it is a certified cable. And the best possible solution is to use a pre-terminated, certified, and rated jacket and applicable connector, be it an RJ45 or an M12 Ethernet connector, which we see here. The one on the left is an 8-pin X code. It supports speeds up to 10 gigabit. And the one on the right supports 100 meg speeds, as it only has 2 pair or a 4-pin connector. Next, we're going to talk about the benefits of fiber. Fiber resolves category cables 100-meter distance limitation. It is immune to RFI EMI, lightning, differences in ground voltage potential, and one needs to keep in mind that when utilizing or deploying fiber, the respective optical elements need to match the fiber type and the data type. The connector types are generally irrelevant. So in this case, what we have here is we have a switch. It has 3 RJ45 ports, and it has a single 100 megabit multi-mode fiber port. It is connected to another device, which then also will need to communicate at 100 megabit. So we have a match on fiber optic ports. And because the fiber optic ports are multi-mode, the fiber itself needs to be multi-mode. The fiber optic elements themselves can either be embedded on a PCB, typically what you will see for most 10 and 100 megabit applications, or added into the switch in the form of a SFP. SFP stands for a small form factor pluggable. One also needs to keep in mind that the data speeds massively affect the distance. The higher the speeds, the shorter the fiber optic segments that you can have. This is especially true with 100 megabit multimode versus 1 gig multimode. So 100 megabit multimode can traverse a far greater distance than can 1 gig multimode. And just to illustrate how much of an impact the speed and distance correlation has, is a customer with an existing installation of OM2 fiber, which is a 50 micron fiber, which is rather prevalent in the industry, is not going to simply be able to assume that he's going to be able to upgrade his network from 100 megabit to 1 gig, unless the longest fiber optic segment is less than 550 meters. This too is why many customers simply to take the distance issue off the table will migrate their network or any new installations over into single mode. And with single mode, as you can see, the distance limitation between 100 meg, a gig, even 10 gigabit simply is a moot issue. There are different types of fiber optic connectors, but inevitably every fiber optic port consists of two connectors, both a transmit and a receive. It also needs to be kept in mind that the transmit of one device will connect to the receive of the opposite end and vice versa. This crossing over is typically done within a patch panel, which all fiber optic applications should utilize. Though some SFP sockets may support dual speeds, the optics themselves are fixed speed and type. So if you have a SFP socket as shown here, that indicates that it supports both fast Ethernet or gigabit SFPs. It is the SFP that will drive the speed as well as the type of fiber that is then supported. There are also things called combo ports. So combo ports is a combination SFP and RJ45. The one that is utilized will then dictate as to what that combo port is, typically with the SFP overriding the RJ45. Next are the connectors. First off, we have LC. This is probably the current trend in the industry. LC connectors are typically utilized for gigabit speeds and higher. They usually require the use of an SFP transceiver. So very often we will see a request for quote for a switch that will have a SFP socket, but the customer or the engineering firm that has put together the specification will have forgotten to include the SFP. So do keep in mind that the SFP is going to be an additional, albeit minor, cost to the entire bill of material that you will then need to purchase. Additionally, you'll notice that the transmit and receive connectors are held together with a duplexing clip. This simplifies the insertion and extraction of the connector and also ensures that the likelihood of accidentally flip-flopping the two is reduced. Next, we have the SCs. SCs are typically utilized for 100 megabit, and the optics are almost always embedded in the device's PCBs. So you will likely see a switch with an SC socket embedded in it. This is not something that can later be added onto the device, so do be aware as to what your fiber requirements are going to be, and to whether it is then multi-mode or single mode. Next, we have the STs. These are typically thought of the stab and twist. It's a bayonet style connector. These are predominantly utilized in legacy installations or installations with extreme vibration and or shock. Here too, the optics are almost always embedded on the device's PCBs. Last but not least, we have the MTRJ. This is something that should be avoided if at all possible in industrial applications. This is a connector from the enterprise world or the office world. Here too, the optics are usually embedded on the device's PCBs. The reason that we encourage you to avoid the MTRJ is because it is very difficult to terminate in the field due to its small size. There are two individual strands in one connector, making it very difficult to wire out in the field. Next, we're going to talk about patch panels. Patch panels are a means of protecting your vital structured cabling, and this is not just for fiber. It allows for the termination of incoming copper and bulk fiber and then distributing it from there. It's ideal for the conversion from one connector type to another via the use of a patch cable with different connectors, as shown here. In this case, we have the SC connectors on the fiber optic patch panel and a LC that could either be inserted in a device or in a switch. So to facilitate this connector change between the two, it is as simple as using a SC to LC fiber optic patch cable. Patch panels also permit for the creation of fault-tolerant topologies from linear ones or where previously not possible. As shown here, we have a linear topology. The downside of a linear topology is that if there were an issue with, for example, this switch right here, all of the devices hanging off of these other switches will no longer be able to communicate to other network segments. The workaround for this is to utilize the patch panel and plumb the fiber, assuming there are unused, also referred to as dark fibers, that allow you to then reroute those cables within this patch panel. And all it would take is a patch panel at every location, and one can now have a fault-tolerant topology such as this, so that if you do lose comms on that one switch, you only lose the devices that are directly connected to it. All of the other devices connected to the other switches are still able to communicate. Wireless is not something that should be utilized for time-sensitive or mission-critical communication. And the pros and cons for some of the most common wireless frequencies, such as 900 megahertz, is that while it has a relatively low data rate, it is very good in terms of distance. It's also most commonly utilized for serial and proprietary data communications. We then have 802.11. This is Ethernet based, 2.4 gigahertz. You do get a very good data rate, relatively good distance. We then have the 5 gigahertz spectrum, also 802.11, meaning that it's Ethernet based. And you do have very good data rate, good distance. And then you have cellular. Cellular obviously is heavily reliant upon the carrier to determine the data rate, as well as the protocol, whether it's 3G, 4G, LTE, and obviously the cell tower load. The range directly depends upon the distance to the nearest cell tower. Best practice, regardless of the wireless frequency or technology that's utilized, is to invest in a site survey to determine interference, especially in applications that are not line of sight or distances that are greater than 500 meters. Not to mention those that are prone to fault with multiple packet losses, which is very common in wireless applications. For 802.11, the ambient RFI EMI noise, the distance between radios, and throughput needed will dictate the frequency as well as the standard and antenna type that's utilized. When deploying wireless Ethernet, one can use the same SSID name as well as wireless encryption to ensure seamless roaming from one access point to the other. The only stipulation is that one should try to prevent overlapping the channels of the access points. So as shown above, we have one access point overlapping another access point, yet the channels that are being utilized are different, and as a result they're going to have slightly different frequencies, preventing interference of each other. One should avoid crowded channels used by other radios. This is easily done by using freely available apps that can be downloaded either for PCs or for Android smartphones. This will allow for the tailoring of the channel and frequency used by one's access point. We also caution customers from being lured in by manufacturers' claims of excessive wireless speeds, as these may only hold true in ideal laboratory conditions. Ideally, find a vendor that has a throughput calculator that allows you to determine what your overall estimated throughput would be depending upon the distance, the antenna type used, as well as length of antenna cable. For new installations, lean towards 802.11n and AC. Avoid cutting-edge new standards. Both 802.11n as well as 802.11 AC are established protocols in the industrial space. Both support multiple spatial streams, which means they both have high throughput and very good distance. Both of these also support 5 GHz, which is a less crowded frequency range. Also, be aware that you will require an external antenna to achieve any reasonable distance. Also, remember to place the radio as close as possible to the antenna to limit any loss as a result of the antenna cable. And for optimal placement, consider a PoE powered access point, or even one that is IP67 that allows you to position it outside of a control panel. So now that we have some guidelines about the media, here's what you can now prepare for. As far as a standalone machine, this is something you should easily be able to deploy. An application that is networked as part of a small production cell, that too is something that you should be able to do. Stepping it up a notch, looking at this machine cell networked into the rest of the production line, this is a little bit more challenging. And we then have an entire plant-wide network that you can then network this into and have it accessible by the rest of the plant. These are all topics that we're going to cover in the next video of this series. Thanks for watching, and please join us for the next video.